Good morning, folk. My name is Murray Jones, and today we're going to have a look at how we can use metal oxide field effect transistors in circuits. I've already uploaded a video on an intro to MOSFETs, where we had a look at some of the schematics, at the internals of the thing, we had a look at the guts. Today we're looking at the gizzards. It's all well and good to be able to say, look, I understand how MOSFETs work, I can draw a schematic of them. But we're not physicists, we're engineers, we need to be actually able to build something with them. We're going to have a look at amplifiers, we're going to have a look at biasing, and we're going to have a look at a bit on current mirrors as well, and how that all fits together with these metal oxide field effect transistors. Right, so first, a brief recap from the last video. It's worthwhile having a watch of it, it's important background for today, but I'm just going to mention it again just to get it fresh in your head. So we had a look at this trusty stick. We had a look at this structure for an N-type metal oxide field effect transistor. We've got this N-type doped silicon on the source, same on the drain, that's doped with something like phosphorus, and then we've got P-type in the channel region, which is doped with something like boron. We can model the central part of this metal oxide field effect transistor essentially like a capacitor. So we have charges that build up on the gate, and that draws in negative charges from the substrate into the channel region. When we have enough charges built up in the channel region, we have enough mobile charge carriers, and a current can then flow, because we put a bias, a positive to negative voltage, sideways across this channel region between the drain and the source. So this is like a voltage controlled resistor. The voltage on the gate controls the resistance between the drain and the source. So we can abstract this a step further and look at the gate to the source. The source is usually tied to the body here, so we can leave the body out of this diagram and say, okay, there's your plus, there's your minus, two lines, capacitor. That's essentially a model of this capacitor here between the gate and the source. Now for the current flowing through the channel region, we can model that as essentially a consistent current source between the drain and the source, and we saw the equation for that yesterday, and we'll see it many more times today. Right, now that's all well and good. Like, it's great to be able to say, look, here's a schematic of a metal oxide field effect transistor. I know where the N and the P regions go, and you know, that's a really useful starting point. You can see how these things are actually built. They're built with lithography machines, which are absolutely fascinating in and of themselves. Like, they'll lay down a base layer of silicon, then deposit on, say, N-type silicon, then use a really precise laser to erode away the bits they don't want, leaving just a couple of chunks of this N-type silicon. Then they'll deposit a flat layer of P-type over the whole lot, erode away the bits they don't want, and they'll be left with this NPN structure that looks pretty much like that. It's absolutely fascinating. But that's not the point of today. The point of today is this little bit over here. So we can abstract this whole thing one level further to use it in circuits. Like, it's all well and good to be able to say, look, I can draw a diagram, but look, we're engineers. We're not physicists in this course. I love physics. I've got most of a physics degree, but here we're talking about engineering, and we actually need to build something with the thing. And for that, we need our models to be as simple as possible. We don't want to be tracking individual electrons. We want to track a drain, a source, and a gate in between them, and that's about it. Right. So the other really key thing we saw yesterday was the behaviour of this. This is the drain current, so there's only one current in these MOSFETs. It goes from the drain to the source. Remember, the gate draws no current, and that's what makes them great. Makes them extremely efficient. I waved around a CPU. You can fit 400 trillion of the things in there, all because the control from the gate draws no power. It's done with the field, not the current. Now, there are two regions we really need to consider here. The triode region, which is where we have, you know, fairly low currents and voltages all round, and the saturation region, which is where the thing really gets going. So increasing the drain to source voltage is no longer changing the drain current. We've got as many electrons flowing between that drain and that source as the thing has the physical space to support, right? And that is the key point. And we've got this threshold here. So when the drain to source voltage is greater than the gate to source voltage, remember gate, the bit in the top that does the control, minus this threshold. And that threshold is a result of the fact that you need a specified number of electrons for this to happen. Like, you can't just do it with a couple. You need pretty much a continuous row of the things. And there will be a specific voltage on the gate at which you've drawn in enough of them. And that'll be a property of the transistor. It'll be about 0.4 to 0.7 volts or thereabouts, depending on your individual device. For this one I've got here and waved around yesterday, like, I think it's about 0.4 volts. Right. Now this is the really important point that we saw yesterday. Saturation region, that's where all of the interesting things happen. Triode region, look, only use it if they actually tell you you need to. Everything interesting happens in saturation region. It's just, you know, that's where it is. Like, and let's have a look at why that is. The reason we like to use saturation region is because of this square here. So the triode region equation doesn't have that square, but this square means that we get a quadratic change in the saturation current as a function of the gate voltage. So we're actually squaring it, which is a lot more powerful than this just linear relation, hence why they call it a linear triode region. It's a lot more powerful than that, because we have that square, and that square allows us to do amplification. Yeah, as the lecturer in my course said during one of the lectures, you should make an intelligent guess as to what region the MOSFET is in, and then verify your guess. And you do need to verify the guess, but you know, you don't need to guess what the intelligent guess should be. The intelligent guess is saturation region. Any other guess is unintelligent. Like, this is where it's at. Righty, amplifiers. Let's just dive on into how we can amplify using a MOSFET, because that's a really handy thing to do. Like, we have a signal, we have a little signal, and we want to turn it into a bigger signal. You know, it might be something from a piezoelectric in a microphone. You've got this oscillations in sound waves. Generates a tiny little voltage from the dipoles aligning and anti-aligning. And we need to turn that voltage into something we can actually do something with. Say it's a megaphone. We need to amplify that to output at a much larger amplitude. This is something that MOSFETs can do really well because, as I said, they draw essentially zero current. The switching is done with an electric field. And to do that switching, we got to be in saturation region, because that's where we've got this square, and that square is doing the brunt work here. Like, it's absolutely carrying the team. So when we adjust this gate to source voltage, we adjust the current from the drain to the source. So that's the ID term, and it's dependent quadratically on voltage between the gate and the source. So when we adjust the current through here, this is all one circuit. We change the current through the resistor. Ohm's law, V equals IR. The resistance isn't changing, so that means the voltage at this point will change. And that's where we can measure our amplified output, because what we want to measure is a voltage, right? We're trying to amplify a voltage, not a current here. And this is where we're going to measure it. So the input on the gate, output here, like so. Right. Let's put some numbers to that. Transconductance. So what we can do, we want to know exactly how much this current at the drain, current through the whole thing, only one current, remember, we want to know exactly how much that current changes with a change in voltage on the gate. And the way we can do that is partial derivatives. Partial derivatives, look, if you haven't seen them before, don't panic. They're just behaving like regular derivatives today. They can do some weird things on occasion, but today it's basically just doing what a normal derivative would do. Imagine those are D's. So we take a partial derivative of this expression for the drain current, remember, in saturation, always in saturation, with respect to the gate source voltage here. Remember, VTH, VTN, same thing, they're just a threshold voltage for when this thing turns on, and this we talked about yesterday is the channel length modulation parameter. So we can take this partial derivative, we bundle all these constants up in a thing that we call beta, and then that gives us this relation here, and instead of writing it in terms of the partials every time, let's write it in a term called GM, right? GM, we'll call it the transconductance. Big fancy word. Essentially it's just the dependence of current on control voltage at the gate, right? That's basically all there is to it. It's how much this current through here depends on that voltage there. Right, now this expression it's slightly awkward to deal with. Like, it's okay, but there are a few different things we can do with it from here to make it, you know, perhaps simpler, perhaps not, depending on your point of view. There's exactly 3 different things. If we don't care about channel length modulation, if this lambda is 0, then we can just use this equation here. This is usually the easiest. It's just got a bunch of constants out the front, the gate source term. Look, it's literally a direct dependence on the control voltage. If we want an exact expression that does deal with this lambda term, the channel length modulation, then we need this one over here, right? This is an expression that's got double the current divided by this gate to source minus the threshold. That's generally an unwieldy expression to use. It's not one that gets used an awful lot, but it's important to know if you actually need to calculate this thing exactly. Now, our other option over here is this one here, which still has our constants out the front, but it just throws the current in there. So if you know the current, this one's an easy one to use. Like, if you know the current and nothing else, this one's your go. And yeah, it makes the lambda term your problem because it's wrapped up inside this current. Like, it's up to you whether you include the lambda term in this current that you know when you're doing that calculation for it. You know, you've got to be a bit careful with this one, but if you know current, it's an easy one to use. Right, the small signal model. So we have this expression for GM, the effect of the gate source control voltage on the drain current, right? We've established that. That's okay. So now we can be a bit clever about this. We've already seen this model here for the metal oxide field effect transistor, right? We've got the gate to the source, we've got this essentially a capacitor in between them, and we've got this big fat current here. But if we're only dealing with small signals, if we're only dealing with the really small signals in this situation, then we can simplify this. So delta ID is a small change in current, delta VGS is a small change in voltage. And by convention, we just use a lowercase v for a small change in voltage, right? So now if we multiply this transconductance by our small change in voltage, we will get a small change in current. And in the small signal model, everything is small. So we multiply this by that, and that gets us this expression for the current, which is much smaller and much nicer to use than this whole big thing, so long as we've only got a really little signal, which is something that we quite often have. For example, the input from a microphone, like the literal sensor that converts sound waves into voltage, the piezoelectric, is a really small signal input. So this is perfectly fine for that situation, right? Now, there is, however, a small catch to this. Our model looks quite nice there, but this idealization that we get a perfectly flat line here, no dependence on drain current with a change in the drain to source voltage in the saturation region, isn't quite true. There is actually a small slope to it, which is essentially due to a resistance like V equals IR. It's a non-ideality in the system, and it actually is cropping up due to our channel length modulation again. You know, channel length modulation, it's one of those things you just have to kind of deal with when it shows up. And fortunately, there's an easy way to deal with this one. We've got this extra resistance term here that's creating this slope. So we just model it as a resistor here, and its resistance will be 1 over lambda times the current. You can work that out with essentially taking the gradient of this line and then throwing Ohm's law at it once or twice, but just take their word for it. It is an approximation, but it's a good one. I've never seen a question that doesn't use that approximation. So we'll model our whole small signal model with this one extra resistor, just to account for this if we need to. And listen, if we don't need to deal with channel length modulation, then this resistor is just infinity, okay? An infinite resistor is an open circuit and it goes away, we ignore it, right? But it's there in case we need it, which is important. I'm writing these titles in lowercase because all the notation for small signal model is lowercase, right? So, we've had a look at this small signal model. Now let's look at how we actually build this into an amplifier. And you'll see the term things like common source amplifier. Common just means ground, because ground is the same between every point in the circuit. Like every ground in a circuit is the same ground. You can't have two different grounds, or at least you jolly well shouldn't. So common ground, same thing. Common source will just mean that the source is the part of this MOSFET that goes to the ground. And once again, we always got to be in saturation mode, because that's where that square is, right? Now, this is an interesting point here. We've got this whole system. We have our input here, and we've figured out that it's going to have an amplified output here because of the squared dependence on current through this bit, the resistor, Ohm's law, and so forth. So let's break that apart a bit. We have our input here, which is an oscillating. It's a really small input, and that goes to our gate. Then we have essentially a capacitance over here, a voltage between the gate and the source. Now, we've already seen this part before. We've seen this modelling the current that's going from the drain to the source through that channel region. We've just explained this little resistor here that we throw in for the channel length modulation. Now this is the resistor on the drain. And you might be thinking, well, what on earth is it going to ground for? Wasn't it just going to this power supply, which could be like 5 volts or something? Like, what are we doing? Why do we just ground it? Now this is where I've got a demo. Like, look at me, I've got a demo. So like, anyway, my demo consists of this bit of rope tied to this chair, which I'm going to need a taller chair. Hold on. Oh, do I have a taller chair? Beep, beep, beep. There. Okay, demo time, lads. Right, this is essentially a potential, right? It's got a gravitational potential that's different to an electrical potential, but practically speaking, it's a potential, and that's what's important. So, if I have this whole rope up here, I'll have so many joules of gravitational potential energy. Up here, it's equivalent to 5 volts. So that's the analogy, and that would be a large signal analogy. But what I can do is, if I can shake this up and down like so, small signal is just a tiny vibration through this. There's your small signal, right? Now, this small signal, it does not matter one iota whether I do this down there or whether I do it with, you know what, I need a bigger stick. I think it's a rudder pole off a 16-foot skiff. A very nice clove hitch. Okay, right. It doesn't matter one iota whether I do that way up here or down at the, more normal level, okay? It's, as far as the small signal is concerned, just the vibrations in this rope, the vibrations are the same whether they're way up here or, I can slide this. Now that's very nice. Or down here. The small signal doesn't depend on the position of the large signal, right? Large signal low, large signal high, small signal doesn't care, right? The interaction between it and the pole is the same in either case. So the small signal, if it goes through to the ground, will get sucked out by the ground just the same way as it would be if it went into this 5-volt source. Like, it doesn't matter how high the rope is on this pole. When the small signal, the vibration, gets to the pole, it behaves the same way whether it's down here or up there, right? So instead of having this resistor going up to a VDD, say 5-volt source up here, I can just have it go straight to the ground, because we're only worried about the small signal, and the small signal doesn't care whether it goes into a ground, runs into a pole way down here, or whether it goes into a 5-volt, runs into a pole way up here. Like, it's essentially the same in either case as far as the small signal, the vibration in the rope, is concerned. And that is why we can put this resistor here when we're making this model. Right. Now the input and the output, the resistance. The input resistance here is going to be the resistance essentially across this gap. Open circuit resistance is infinite. So the gate is going to draw no current. That's kind of the point, right? The whole point of metal oxide field effect transistors is that they have infinite input impedance. They do not take in current as part of their control signal, which makes them incredibly efficient. The output resistance is going to be for this whole amplifier, including this resistor here and the transistor itself, is going to be these two terms in parallel, right? We've got to go from over here, from the input over here to the output over here, and it's got to go through these two resistors because it can't go backwards through this current source to get to the output. Right, so it's going to be these two in parallel, just the standard formula for the resistors in parallel in an ideal transistor. The R0 term is going to be infinite and we'll just have the RD, but just to cover our bases in case we need this channel length modulation, we leave that one there as well. Right. So, now let's have a look at the amplification factor from here. The amplification factor is, for a small signal, the ratio between the output amplitude, which is, how much my rope waves, the output amplitude of the waviness, versus the input amplitude, which is going to be a smaller waviness of the rope. They're both small signals, so compared to the actual altitude of the rope, they're both small, but one of these amplitudes is larger than the other, and the ratio between them is this amplification factor, which we can get by taking GM, multiplying by the voltage, throwing Ohm's law at it a few times, and we get this expression here, which is a very trusty expression. You don't need to know how to derive it, just know how to use it, and how it fits into this model with the transconductance and these two resistors here, right? Okay, so the mechanism that we've been looking at up to this point is the common source amplifier, and that's when you have this output, the source, going to a ground. But what if you don't? There are actually other types of amplifier you can do with this, and one that's used a fair bit is called the source follower. Now this is essentially just used as a buffer. It keeps the voltage essentially the same between the input and the output signals. The output will actually be slightly smaller, but not by much. It's approximately 1. But you can get a fair bit more current out of it. And the way it does that is by having this, it's called a load resistor to the ground, input, output. It's essentially the same configuration, except instead of having our resistor and output above the MOSFET, we have it below. And that means we're dealing with a slightly different situation, because over here, we still have the same thing with the input signal and our infinite input resistance, of course, because, if we didn't have infinite input resistance, it wouldn't be a MOSFET. But for this output scenario, we have a slightly different case. Because we have this output position on the other side compared to where it was before of this current term with the transconductance in it, that means we get a 1 over GM factor. But the resistors are still in parallel, which is quite interesting. But when you look at it, from this point to get to ground, we can either go this way to ground, or we can go this way to ground. So they're definitely not in series, right? This resistor is definitely not in series to that from the point of view of this, because we've got two totally separate paths to get to a ground. That means these are in parallel, and that's where that calculation comes from. And that's for the source follower amplifier. It's not too tricky. Right. Now we're going to have a look at MOSFET biasing. This is how you can make dead sure that the thing is in saturation mode. Because all of what we've been talking about only works if it's in saturation mode, right? If it's not in saturation mode, it isn't going to work. It's got to be in saturation mode to make any of this work. And on a vaguely unrelated note, look at this goose. Seriously, look at this goose. It's crazy. I didn't distort this image. This is apparently the legitimate proportions of a wild Canadian goose. Moving on. MOSFET biasing. So this is how we can make sure the thing is in saturation mode. And to be in saturation mode, we've got to have the drain source voltage, that's the voltage from one side of the thing to the other, be greater than the gate source voltage, that's the voltage on the gate that's actually doing the controlling, minus this threshold. And we talked about the threshold last time. That's the threshold for when you've got enough electrons in the channel to do conducting. So the first thing we obviously need to control is the gate voltage here, right? Gate voltage. So we can do that just with a good old voltage divider. We've seen those before, and that can control our gate voltage. And we might have a small signal input anywhere on this circuit. This is talking about large signals to make sure the thing is in saturation mode so that our small signals can work, right? So that can control our gate voltage. But, you know, we've still got the drain voltage and the source voltage that we're a little bit iffy about here. We could have a way big current flowing through this thing because we've got no resistors at all. So we throw in two more just to give us full control of this circuit. We know exactly what's going on. And this whole thing is called 4 resistor biasing. No prizes for guessing why. 1, 2, 3, 4 gives us full control of what's going on here. The voltage between the gate to source, the threshold is just constant. The gate to source is the one we care about. That's going to be the voltage at the gate minus the voltage at the source. Here is our expression for that voltage divider we've set up over on the left-hand side here. And then we have the current. There's only one current over this side through the MOSFET. That current times this resistor on the source. That's just working up Ohm's law. That's going to give us the voltage at the source here. And that's the expression for the gate to source voltage. Now, if we substitute in some of these terms and some of the current terms, do a whole lot of algebra, it spits out that thing. Lo and behold, it's disgusting, but it's there. You don't need to know how to derive it, just put it on your formula sheet. Again, we've wrapped up a bunch of the constants in a beta n. We've got the threshold. Here's our voltage divider. Yeah, this is the expression for 4 resistor biasing. This is basically the one you're going to need to use to check that this thing is in saturation mode, which is going to be a very important thing to check down the line. Right, that's 4 resistor biasing is essentially, it's the best way to bias these. It's the most reliable, it's the clearest to see, but there is actually another way, and that is self-biasing. So this uses one less resistor, but it's a bit more finicky. It gives us a bit less exact control. Look, if we analyze this circuit, we can step through it. We can say, this current here, there's only one current in the circuit, times by the resistor at the drain. Ohm's law, that gives us the voltage to here. This part has no current in it at all, so there's going to be no voltage drop across this resistor. By definition, remember, gates don't draw current. So we've got the voltage to here. Now we take the voltage between the gate and the source, this VGS term, that gets us down to here. The resistance on this source resistor times by the current again, which is flowing through this MOSFET, gets us down to here, and we've just gone that from top to bottom, but the whole thing at the top is the total voltage. Right, that's just Kirchhoff's voltage law in a nutshell. But if we actually work this through, then we can figure out that the drain to source voltage, so again, because there is no current going through here, the drain to source voltage is going to be the same as the gate to source voltage, which means it automatically satisfies this condition, so long as there's nothing really weird going on with this R, so long as the R is smallish, right? And that's the dangerous part. It's easy to get that wrong. Like, be careful of it. But in most cases, this arrangement is going to guarantee you, a mostly guarantee, that's not much of a guarantee, is it? But, you know, if you have a fairly small resistor on your source, then this arrangement is going to get you a MOSFET that is in the saturation region and that you can use for amplifiers. Right, now this gives us some very interesting things we can do. Because we can essentially take something like this, which is, you know, more or less what we just saw on this side over here. It's more or less a self-biased MOSFET. We can rig this up in such a way that the ratios of current on either side of this circuit depends only on this W1L parameter. Remember that's the dimensional parameter we saw yesterday. So we can rig up two transistors with different dimensional parameters, different W1Ls, and know that the current from one side to the other will just be the ratio of W1L. And that is really handy because it means that we can have a really well-defined current over here just by taking these ratios. So we could rig this up in such a way that if we've got an amp over here, we can have 3/5 of an amp over here and know that that's what's going to happen. So this is a basic principle that underlines a lot of current sources, and it's really handy to know. And yeah, basically all you need to do to know it is know how to use that equation and plug it in, right? There's nothing that tricky in it. Okay, key point of today. All of this has to be in saturation region. If we want to do basically anything with a MOSFET, it's got to be in saturation region. The couple of times that we actually use the triode region, look, they're rare and they'll tell you to use the triode region. The whole thing, you do actually have to check that it's in saturation region, but that's basically just a formality because it always will be. But you'll lose marks if you don't, and you know, they might throw us a curveball where it isn't, but practically speaking, it jolly well should be. This is the condition for saturation region. We do a whole lot with this biasing for the sole point of making sure that it's in saturation region. Right, that's the takeaway. So long as you know how to get a MOSFET in saturation region and what it does once it's there, you can wield these things, right? And that is all. That is all for today's presentation on MOSFET circuits. Will we do another one? Look, maybe. If you guys find this useful, let me know. I've had one request for transfer functions. If I get, half a dozen, I'll do one on transfer functions. There wasn't a lot of take up on the suggestion of, setting up a document cam and doing practice problems when I suggested it last time. But, maybe everyone's just shy, so, if you want me to set up a document camera and do practice problems, say so, I can do that. Yeah, anyway, that is it for today. Longer video than last time, but I hope you find it helpful, and have a wonderful day.